Okay, so let me review kind of the basic idea of induction that we did last time. So the basic idea is the ladder idea, right? I climb in on the first rung, n equals 1. Then I prove that if I'm on any rung somewhere, I can always climb up one more rung. Those two things combined mean I can climb the whole ladder. Because if I can get on the ladder and I can always go up one, then I can climb the whole ladder. Okay, so that's the idea of induction. So we showed two things, right? We showed the statement is true for 1, our base step, and we showed that the statement, if the statement is true for n, then the statement is true for n plus 1, our inductive step. So we did those two things over and over. Okay. Sometimes that's not good enough. So we need the strong principle of mathematical induction. Instead of just the PMI, we have the SPMI. I know. Okay, so notice the first part is the same. It's true for 1. Okay, so I can get on the ladder. But the second part's a little different. Instead of assuming it's true for one specific n, I'm assuming it is true for every single number up to n. So instead of assuming I'm on a rung of the ladder, I'm assuming I have covered every single rung up to here. Okay, you guys see the difference? Then we prove it's true for n plus 1, that I can go up one rung. Okay. All right. In order to do some stuff with this, we're going to use something called the well ordering principle. I have here sometimes called least natural number principle. Basically, it's a common sense thing that if I have a set with a bunch of natural numbers, one of the things in it is the smallest. Okay. If I have a set with a bunch of natural numbers, one of the things in it is the smallest. Think of it this way. Well, if you pick a bunch of natural numbers, let's say you take, I want 1,000,000, and then I want 13, and then I want 17, then I want 10 to the 10th, then I want pi cubed, right? One of these has to be the smallest. I can't make a list that keeps getting smaller and smaller and smaller and smaller without stopping, right? Does everybody see that with natural numbers, what I'm saying? This is not true with rational numbers, because with rational numbers, I could do 1, 1/2, 1/3, 1/4. There I could make a shrinking list without ever stopping, okay? But with natural numbers, at some point, you have a smallest. You can't go any smaller. You guys see the difference? Okay. So let's look at some proofs where we use these ideas, okay? Every natural number greater than 1 is either a prime number or the product of prime numbers. This is a part of the fundamental theorem of arithmetic that you learn in elementary school that basically says, hey, take your number, you can factor it into primes. Okay, you remember doing kind of factor trees in elementary school, right? You take 120 and say, oh, well, I'm going to make it 12 and 10. I'm going to make it 2 and 6 and 2 and 5, right? So I got a product of a bunch of primes. Okay, you guys, you did that in elementary school, right? Okay. Yeah. So did it matter that I started with 12 and 10 versus starting with 60 and 2? No, you get the same thing. So the fundamental theorem of arithmetic says not only is it a product of primes, but that product's unique. We're not going to prove uniqueness. We're just going to prove, yes, you can split it into a bunch of primes. Okay. All right. Here we go. So notice it starts every natural number greater than 1. So what's my base step going to be since I can't be 1? 2. Okay, so proof. Let's do our base step. Again, we're labeling base and inductive step. In your upper level classes, they may not label them. All right, we'll say Note that n equal 2 is a prime number. So, and that's it, right? I want to say every number is either prime or a product of primes. Well, he's prime, done. Okay, so that's our base step. Inductive. So here's our inductive hypothesis. We're going to assume every natural number from 2 to n is either prime or a product of primes. Product of primes for some n in the natural numbers. So I got on the ladder at n equals 2, and now I'm saying I have climbed up to some point n. I have hit every single rung from 2 up to where I'm standing at n. Okay. Whereas in our normal induction, we would have just assumed n itself was prime or a product of primes. Okay. All right. So let's consider n plus 1. So basically 2 things could happen here, right? N plus 1 could be prime or it could not be prime. Those are the options. If n plus 1 is prime, we are done. So that's kind of case 1. It's just so short, we're not even writing it as its own separate case. If n plus 1 is prime, that's what we want. It's prime or a product of primes. So assume n plus 1 is not prime. Well, it's bigger than 2, so if it's not prime, it's 2 or bigger, I should say. So if it's not prime, what's that mean? It's composite. The only other not prime is 1, right? So assume n plus 1 is not prime. This means it is composite. Thus, there exist A and B, the natural numbers, with 2 less than A less than n plus 1, 2 less than B less than n plus 1, and n plus 1 equals A times B. I should say less than or equal, sorry, at the 2, less than or equal. Right, so if it's composite, I can factor it into stuff that's not 1 times itself. That's what we're saying there. I factored into 2 things that are not 1 times itself, okay? But what did we assume about any number between 2 and n, which these have to be between 2 and n? Yeah, it's either prime or a product of primes. Well, if they're prime, then n plus 1 is a product of primes, right? It's prime times prime. If one of them's prime, one of them's a product of primes, it's still a bunch of primes multiplied together. If they're both a product of primes, it's still a bunch of primes multiplied together. No matter what, that is a bunch of primes multiplied together. You guys see that? So if A is a bunch of primes, then I could replace A with his bunch of primes. If B is a bunch of primes, replace B with his bunch of primes. Now n plus 1 is a bunch of primes. So by the inductive hypothesis, we can write this out rigorously. A equals, put a big capital pi. This means multiply over and over. Let's use I equals 1 to k of pi. And B equals capital Pi, I equals 1 to L of QI. For PI and QI prime. You could have written this out in words, but this is the symbol way of saying A is a bunch of primes multiplied, B is a bunch of primes multiplied. Does that make sense? So apparently A split into K different primes and B split into L. I shouldn't say different, but L primes. Some of them may be repeats. Okay. All right. So m plus 1 equals product I equals 1 to k pi times the product I equals 1 to L qi, which is a product of primes. Therefore, by the, I'm going to put SPMI. We could put PMI, but technically we use the strong principle of mathematical induction. This is true for every n in the natural numbers with n greater than or equal to 2. This would not have worked if I'd used the regular principle of mathematical induction. If I had only assumed n worked, when I factored n plus 1, my A and B would have been too small, right? I needed every single number less than n plus 1 to work. So when I factored it, I didn't care where those factors hit. That inductive hypothesis applied, okay? So that's the big difference here. You use the strong principle of mathematical induction when you're dealing with m plus 1, you end up with stuff somewhere below it, not just necessarily 1 below it, okay? But it's still the exact same idea. All right, any questions on example 6? All right, so let's look at example 7. And this is going to be regular mathematical induction again. So prove that for any natural number n, 6 divides nq minus n. Let's do some scratch work. It says for any natural number n, so what's my base step going to be? 1. All right. Well, 1 cubed minus 1 is 0. 6 divides 0. Yes, that's okay because 0 does equal 6 times some integer k. So we're okay. All right. Here we go. So in our inductive step, we're going to assume 6 divides n cubed minus n. Or in other words, right, n cubed minus n equals 6 times k, some integer k. Okay, now we want to consider n plus 1 cubed minus n plus 1. Because I want to see what happens if I put n plus 1s in there. Nope. When you multiply that out, I'm going to skip some steps in algebra, but when you multiply it out and rearrange it, oops, go back. Okay, you get n cubed, let's see, plus 3n squared plus 2n. So I can rewrite that. Well, let me motivate. I want n cubed minus n because that's what I know something about. So I'm going to rewrite this as n cubed minus n plus 3n squared plus 3n. All right. Because the 2n, I rewrote it as a minus n and a plus 3n. Yep. All right, so running out of space. So I'm going to bring it up here. So we have n cubed minus n. That's going to be replaced by 6 times k. 3n squared plus 3n. Well, I can factor out 3 n squared plus n. What do I want the whole thing to be divisible by? 6. So I have a factor of 3. I need a factor of 2. What can you tell me about n squared plus n? Let me put it this way. If n is odd, what is n squared plus n going to be? Even, because it's an odd plus an odd. What if n is even? It'll still be even. No matter what, this will always be even. So what can you tell me about 3 times an even number? It's divisible by 6. Yeah. So we're ready to do our proof. All right. Proof. Let's do our base step. Note that 1 cubed minus 1 equals 0, and 6 divides 0. So this is true for n equals 1. Now let's do our inductive step. Okay, so our inductive hypothesis, we assume there is some n in the natural numbers with 6 dividing n cubed minus n. Then there exists k in the integers such that n cubed minus n equals 6k. All right. Now, so here we go. N plus 1 cubed minus n plus 1. I'm going to jump straight to the form I need, the n cubed minus n plus 3n squared plus 3n equals 6k plus 3 times n squared plus n. but n squared plus n is even no matter if n is even or odd. So n squared plus n equals 2l for l in the integers. We're almost done. Thus, n cubed minus n, or no, n plus 1 cubed, darn. N plus 1 cubed minus n plus 1 equals 6k plus 6l. So 6 divides n plus 1 cubed minus n cubed. Therefore, let me move this up for you. By the PMI, 6 divides n cubed minus n for every n in the natural numbers. If I had more space, I could have written more details in there, but questions on that one? Yes.
Where did the n plus 1 cubed minus n cubed come from?
Oh, that should be an n plus 1, shouldn't it? Thank you. That came from me writing too quickly and not paying attention. Yep. But the key with this one is getting that algebra right, messing with the algebra till you get the n cubed minus n, and then handling whatever the heck was left over till you got whatever the heck was left over to be divisible by 6, right? All right. So let's go ahead. Let's prove the division algorithm for integers. This one's actually going to use the well ordering principle, okay? Which was that thing that said if you have a bunch of natural numbers, one of them is the smallest, okay? We're going to need that to prove this. So let's get a feel for what the division algorithm says first. So A is an integer, B is a natural number. Then there exists unique Q and R. So my proof's going to have two parts to it. I need to show they exist and show they're unique such that this happens. So let's put this in kind of elementary school terms. When you back in, I don't know, 3rd, 4th grade, did something like 16 divided by 7, before you knew what decimals were, what was your answer? Yeah, 2 with remainder 2, right? Forever ago. Do you guys remember that? You say 2 goes into it twice with 2 left over. Okay, that's what this is doing. R is that remainder. Q is how many groups go in. So let me do a different one so we don't have matching numbers here. So if I do 16 divided by 3, I can make 5 groups of 3 and I'll have 1 left over. So what we're saying is that 16 equals 3 times 5 plus 1. Why are we making the remainder smaller than the thing I'm dividing by? Yeah, if my remainder, so in this example, I'm dividing by 3. If my remainder was 4, I could just pull another 3 out of that. Okay, so you stop when you can't pull any more out. So that's what that is. So this looks kind of cryptic, but that's what it's talking about. Okay, is that elementary school division, except we're writing it in this more useful form. Okay, all right. It means, so the exclamation point means it's unique. So like with this example, I said Q was 5, R was 1. The exclamation point means you're never going to find anything else that fits this property. There's only one answer basically when you divide. Yeah. All right. Cool. So let's jump into the proof. This is going to be a long proof, but it's okay. We got this. All right. So instead of using induction, we're going to use the well ordering principle. Okay, and there's a reason the well ordering principle is in this section. So what we're going to do, we're going to let capital S equal the set of all things of the form A minus BQ such that Q is an integer. So basically my A and B are set, right? Because I'm doing A divided by B or whatever. So A and B are set. So I just plug in every single possible integer for Q and I'm going to get a bunch of different numbers here, some positive, some negative, right? So we only want the ones that are negative. So let's, I guess we should add that in. Q is an integer and A minus BQ greater than or equal to 0. So with the 16 and the 3, it would be saying I'm going to take 16 minus 3 times any integer I want, plug in all of those different things. So 1 would work, right? 2 would work, 3 would work, 4 would work, 5 would work. 6, plug in 6, I now have a negative, so that didn't work. But I can go the other direction. 0 works, -1 works, -2 works. So I should be getting lots of things in S. All right. So we need to show that S is not empty so that we can use the well ordering principle. So if A is greater than or equal to 0, then A minus B times 0 equals A is an element of S. Right? It has to fit those two properties. I have to have multiplied by an integer in Q's spot. I did that. And that combination has to be greater than or equal to 0. Well, A is greater than or equal to 0. So, but what if A is negative? I still get something in S. We just got to be more clever. If, ooh, I'm on highlighter. If A is less than 0, then A minus B times A, that's what we're going to think about. A is negative. So what can you tell me about minus B times A? Since B is a natural number, B is positive. So I'm doing, yeah, minus a positive times a negative. So minus a minus gives me a positive overall, right? So this is actually greater than or equal to 0 because whatever A is, B times A is more powerful. If A is 3, if B is 2, that B times A is now 6. So that -3 is counteracted by a +6. Okay, you guys see that? All right. So A minus BA is an element of S. Either way, S does not equal the empty set. So B is a natural number. So the smallest B can be is 1. Yeah. Yep. No, that was a good thought. Okay. So S is not empty, so we can use that well ordering principle. So by the, guess what the abbreviation is for well ordering principle? Yep, WOP, by the WOP. Okay. By the well ordering principle, S has a smallest element. We'll say, we'll call it R. Why? Because that smallest element is going to end up being our remainder. Notice this A minus BQ equals R, right? Look back at this. A minus BQ equals R. So we want that smallest element to be my remainder in that range. So really all I need to show that this R and Q exist is to show that R is in the right range. Because here, since R is an element of S, R is of the form A minus BQ for some Q in the integers. Okay. We want 0 less than or equal to R less than B. Because that would give us the existence part. Then we've shown, yes, there do exist a Q and an R that work. Okay, if R is in the right range, I found my Q and R that work. So let's do this by contradiction. So assume for contradiction, R is greater than or equal to B. Well, what did we say goes wrong if the remainder is bigger than the thing I'm dividing by? So way back when we were talking about up here was 16 divided by 3. What did we say I can do if the remainder is bigger than the thing I'm dividing by? Pull another group out, right? So that's what we're going to use to get our contradiction. So then I'm going to take A minus B times Q plus 1. And that's what we're going to think about because I pulled out another group. So this equals A minus BQ minus B, which equals R minus B. But that's going to be greater than or equal to 0. If R is bigger than B, then R minus B can't be negative, right? But wait, I have something of the form that fits into S, and it's greater than or equal to 0. So now R minus B is an element of S. So, but this means R minus B is an element of S. Why is that a contradiction? Yeah, S has a smallest element. and it is R. We called it R. But I just found a smaller element. So that's our contradiction. So here we go. So I guess we could say contradiction since R is the smallest element of S. Thus, 0 is less than or equal to R is less than B. All right. So we'll finish up this half of the proof. So therefore, there exist R and Q in the integers with A equal to BQ plus R and 0 less than or equal to R less than B. So that's the first half of the proof. Basically, again, to outline what we did, we took all possible things of the form A minus BQ and found the appropriate R that fit in the range we wanted and said, yes, there is something there that has R in the range we want between 0 and B. That's basically what we did. Any questions so far? All right. Well, now we got to prove they're unique. How do we show things are unique? So the exclamation point means we need to show uniqueness, but how do we show uniqueness? I assume I have two different ones and show they're actually equal. So that's what we need to do. So in order to show uniqueness, are we going to run out of room? Is that what you're asking? I don't think so. I think I left tons and tons of space. In order to show uniqueness, assume there exist. So here we go. We have R prime, Q prime in the integers with 0 less than or equal to R prime less than B and A equal to B Q prime plus R prime. So I'm still keeping my same R and Q from the first half. Now I've said, what if there's another thing that worked? I found one thing that worked. What if there's another pair R and Q? So I'll call them R prime, Q prime. That also worked with that R prime in the correct range. Okay. All right. Well, R prime, I guess I should write this. Since R prime equals A minus B Q prime, and R prime is greater than or equal to 0, R prime is an element of S. Because he has the form it takes to be an S, and he's greater than or equal to 0. But R is our smallest, so R is less than or equal to R prime. All right, here we go. Now, R prime minus R equals, well, let's see. R prime is A minus BQ prime minus, and what is R? R is A plus BQ. What's going to happen with the A's? Yeah, they'll cancel because they balance to 0. So really, I can write this as B times Oh, I have a plus where I should have minus, don't I? Thank you. Minus. There you go. B times Q minus Q prime. Don't put your period yet. What do we know since R prime's greater than or equal to R? What do we know when I subtract? What can't it be? Can't be negative, right? R prime's bigger or equal to R, so this is greater than or equal to 0. Okay, but wait, R prime minus R, the largest R prime is B, right? R prime is not any bigger than B. So when I start with R prime and subtract R, I'm definitely smaller than B. So here's what we have. But this means 0 is less than or equal to B times Q minus Q prime is less than B. All right. I want to divide by B. I just need to be sure I'm not dividing by 0 or a negative. Look back at the top. What type of number is B? Natural number. He's not 0. He's not negative. So divide by B with 0 less than or equal Q minus Q prime is less than 1. All right. Well, Q and Q prime are integers, right? So when I subtract them, it's still an integer. But look, I have them between 0 and 1, less than or equal to 0, less than 1. What's that mean? They have to be 0 because that's the only integer in that range. Yeah. So we'll say since Q minus Q prime is element of the integers, we must have Q minus Q prime equal to 0. What's that mean though? Yep. So, well, they don't both have to be 0, but they're equal. Yeah. So Q equals Q prime. So we've shown that the Q is unique. We still need to show the R is unique, right? But that, we're almost there. That's easy. So using substitution, we get, well, remember, A is, let's see, so A is BQ plus R, but A is also BQ prime plus R prime. Well, we just said Q and Q prime are the same. So that's BQ plus R equals BQ plus R prime. So what does that mean? Yep, R equals R prime. Therefore, R and Q are unique. And we could write a closing statement where we repeat the original problem, but there you go. We've shown if I give you an integer until you divide by a specific natural number, there's only one valid answer that has remainder in the range we want. That's what we showed. There will always exist an answer, and there's only one. That's what we showed. Okay. And that's called the division algorithm. If you take a number theory class, you know, you do end up applying this over and over. It helps with GCD stuff because So something that's a common divisor of both A and B will also be a common divisor of R. And so you can use this to keep dropping it down to easier things. Anyway, okay. Any questions? Hey, look, we didn't even take the whole page. Any questions on that? Yes. Mm-hmm. Well, so because we needed the fact that one of these pairs, either Q prime was equal, so I could substitute in, or the R prime was equal, so I could substitute in. I had to get one of them equal before that way would work. Yeah. Yeah. What else on this one? Okay, cool. So we're going to do one more example. But I want to jump to, because we've been talking about it, this fact, we're not going to prove this, okay? But it's not terrible to prove, and you can find proofs online. These three things we stated, they're all equivalent. They all have the exact same truth value. It doesn't matter which one you use, okay? So induction has the same truth value as well ordering principle, has the same truth value as the strong principle of mathematical induction. They're all equivalent. And there are proofs. Typically they go, well, let me think. So 3 implies 1 is easy. I think then from 1 you go to 2 and then to 3. I think that's the normal path that it's proven, but we're not going to prove it out. Okay. So those 3 things, they're all equivalent. That's why they're all in this chapter. Right. And by the way, the well ordering principle, the WOP, here we're talking about for natural numbers, or you can throw in 0. That doesn't change it having a least element. There's another well ordering principle that is less obvious and not always, well, yeah. So there's statements in math, I should say it this way. There are statements in math that we kind of can assume true or assume not true and get different results. The other well ordering principles like that. So be careful if you're looking online. When it says well ordering principle, make sure it's talking about the natural numbers. That's my point. Okay. Let's do another proof by induction. I want to do one with an inequality because this one, the algebra is a little less obvious. Okay. So here it's asking us for which natural numbers is it true? Prove your assertion. So if this were a homework question, your first step would be to pull out your calculator or pull out some sort of program and get a program to run to figure out when this happens. So if you check like 1 cubed less than 2 to the first, yeah, that works. But when you hit 2, 2 cubed less than 2 squared, that does not work. And if you play with numbers, you'll get, it does not work. You get to 9 cubed less than 2 to the 9th, that does not work. The first one that works after 1 is 10. Okay. And then any one after that you check is going to end up working. They start working. And so you go, okay, so maybe 10 is the turning point. So that's where I'm going to try to do my proof from. Okay. So you guys see that, how you could get there using scratch work is just playing with numbers. All right. So here's what we're going to assume what we want to prove. So proof for every n greater than or equal to 10, n cubed is less than 2 to the n. Oh, I guess I need to do more scratch work. Okay. So the base step we've already done. That's my base step is 10. Okay, so we need to assume n cubed less than 2 to the n. Now we want n plus 1 cubed less than 2 to the n plus 1. Well, n plus 1 cubed is n cubed plus 3n squared plus 3n plus 1. So I can replace the n cubed, say, well, that's less than 2 to the n plus 3n squared plus 3n plus 1. But I say, wait, I have to handle this, right? So I'm going to go back up here to the what I want. That can be rewritten as 2 to the n times 2, right? Or 2 to the n plus 2 to the n. So that whole thing there, I need that less than 2 to the n. All right. So here, this is a less than symbol. Yes. So here's how I'm going to be clever. And you would come across this by playing with it a little bit. So I'm going to keep the 3n squared the way it is. But that 3n, I'm going to replace it with 3n squared. And that 1, I'm going to replace it with n squared. And there's a reason I'm doing this. But does everybody agree if I replace n, let me highlight. If I replace n with n squared, and if I replace 1 with n squared, it's now a larger term, right? So the original is less than the new one I just wrote. So that less than symbol is accurate. Okay. Less than 2 to the n plus 7n squared. But how large is n? I guess I should have put equals there because we didn't change anything. How large is n? What are we assuming our base step is? 10. So this 7n squared, that's less than n cubed, right? Because the smallest n can be is 10. Do you guys see that? I basically changed the 7 to be an n, and that made it bigger. But we know n cubed is less than 2 to the n, okay? I know that's kind of crazy. That's why I wanted to do one with an inequality. But it's basically staring at it, messing with it, messing with it, messing with it till I can get it in the form I want. And it can take a lot of clever trying to get it there. We're going to write up the proof, but any questions on the scratch work? Yeah, so the 7n squared came from adding up like terms. Yeah. And then I replaced 7 with n. By my assumption, my inductive hypothesis, it's less than 2 to the n. Yep. Other questions on the scratch work? Okay, let's write up the proof. proof. Base step. Note that 10 cubed equals 1000 is less than 1024 equals 2 to the 10th. So n cubed is less than 2 to the n for n equal 10. All right. So our inductive hypothesis, we're going to assume n cubed is less than 2 to the n for some n greater than or equal to 10, right? Our base step was at 10, so just being a natural number isn't enough. It has to be greater than or equal to 10. Okay? Then, here we go, string of equations. N plus 1 cubed equals n cubed plus 3n squared plus 3n plus 1 is less than n cubed plus 3n squared plus 3n squared plus n squared equals n cubed plus 7n squared, which is less than n cubed plus n cubed. And I'm even going to put in parentheses since n is greater than or equal to 10. So far I've just done the algebra stuff. This is less than 2 to the n plus 2 to the n by inductive hypothesis. Thus, n plus 1 cubed is less than 2 to the n plus 1. Therefore, by the PMI, n cubed is less than 2 to the n for every n greater than or equal to 10. All right, what questions do people have? Do you guys see how to read that kind of downward string of logic? I'm saying this equals this, but then I say, oh, but that's less than that, is equal to that, is less than that, is less than that. Okay, that's how you read it. You could write it in one long horizontal thing as well. One long horizontal string. This equals this, is less than this, is less than this, is equal to this, is less than this. Okay, you could do that. Yeah, so if you get confused by mixing a bunch of signs, you could write a separate sentence for every single step in that equation. You know, which wouldn't be fun, but if it makes your logic clear to you, you know, that's not the end of the world to write a separate sentence for every single one of those. Other thoughts or questions on that one? So in the scratch work, I substituted it like right away, I guess right here. But here I just waited till here to substitute it in. Yeah. Because it didn't really matter when I substituted that first one. All the work was getting that second one. the key with induction is that scratch work, just getting the from the in step to the n+1 step. That's really your key. And typically at this level, you know, the ones I'm going to pick are not going to be too crazy. Okay, but it may take a little playing with it to get it. It might not be instant immediate either. Okay. All right. Yep, but that's induction and the different forms of induction. It's cool.